Good evening, everybody. Welcome to this webinar presented by the IET Anglian Coastal Local Network. We represent IET members in Norfolk and Suffolk in East Anglia, but we know that we get people from not only other parts of the UK, but over the world listening to us on these webinars. So I'm delighted to welcome you all. My name is Ian Buxton. I'm Treasurer of the Anglian Coastal IET Local Network and will be your host this evening. I'm going to be ably helped by George and Kevin. You'll meet those later. So without further ado, I'm delighted to introduce our speakers. We have Dr. Sophie Carpentier and Laurent Ferrand, both from ITER. That's the International Thermonuclear Experimental Reactor. They're speaking to us this evening from the south of France, where ITER is building its large-scale fusion reactor. Sophie is a plasma engineering specialist, and Laurent is the coordinating engineer in the diverter section. I'm sure they'll be able to explain more about their roles during the presentation. Inevitably, in a presentation lasting just under an hour, they'll only be able to scratch the surface of their work, but hopefully they'll be able to give you an introduction to the project, its current status, and then move on to some of the design challenges that they have for the components that are facing the plasma. So with that, I'll hand over to Sophie. I'll stop.
So thank you first for this nice introduction and this proposal, because it's really a great pleasure to give this talk today on the ITER project. My name is Sophie Carpentier. I'm French. I started working for Fusion in 2005, right after my diploma, and I joined the ITER project in 2009. Since then, I've worked in many different topics between plasma physics and engineering, up to the follow-up of manufacturing of components. And my role at present is notably to translate what plasma physicists think can be the loading of this plasma into the internal components for engineers to understand and to specify and to manufacture the components. So I'm always in the middle of these two fields. So we have separated the talks tonight into two parts. I will give you first a very global introduction about ITER project, nuclear fusion, and then Laurent will focus on a much more detailed, concrete example, which is the manufacturing of one of our components, which is the diverter. He will explain you all that. So as we are my first part, as I told you, I will give a very brief introduction of the principle of fusion. I would like as well to give you a bit of history on this ITER project and the fusion in general, with some key numbers to have in mind, which is quite important to understand then the ITER project actually and the challenges posed by this project. I will explain you how is it organized, this international technical project, and as well I will give you a very brief overview of the main progress, the major achievements we have reached recently, and as well some of the difficulties we have met on the ITER project that people may be aware when they read the newspaper. And then we'll switch to Laurent's part, which is, as I told you, a nice concrete example of the challenge of designing some components for ITER. So if we start about nuclear fusion, clearly this nuclear fusion is the source of the light and even of the heat, if we are talking about the solar power, which happens in the universe by the fusion of hydrogen nuclei. And this happens in the universe thanks to high gravitational forces, extreme temperatures, and densities. In order to do that on Earth, we have developed magnetic confinement fusion principle, which consists in the fusion of isotope of hydrogen, the deuterium and the tritium, making fusion reaction and then producing helium and a neutron. And in order to do that on Earth, we need to have a very, very highly controlled magnetic field in order to confine the particles at very high temperature and densities, or low density, but very high temperature. It's always there is a project to make the fusion reactions happening, which is a compromise or the good condition between densities, temperatures, and then as well the confinement time. So why hydrogen fusion is very attractive? This source of energy is carbon-free. That's the main reason. In terms of fuel, the deuterium, this isotope for the hydrogen, is clearly abundant all over the world. You can obtain it from different forms of water. Actually, the process to extract this deuterium from water is quite well known and commonly used in industry. As regards tritium, the other isotope, it's a bit more tricky because you have only trace in the nature. We can extract a bit of tritium for fusion reaction, but the main advantage of a tokamak like ITER is that we plan to actually breed the plasma in tritium to have like a self tritium breeding thanks to lithium on the wall, and then with reaction with neutron you will actually produce tritium. So you will have an abundant fuel supply in any case. Compared to fission as well, fusion is known to have much more limited, long-lived, highly radioactive waste, and it's as well an interesting safe reaction. It's not like in fission where you can have like runaway reactions in chain reaction. Actually, for a plasma, it's much more difficult to get a plasma. A plasma can be as fragile as a flame even. So here the difficulty is more actually to maintain this plasma. And one of the major difficulties that we will talk about today is to actually be able to build all these components. There are big engineering challenges associated to this kind of project. So in order to create a plasma in a tokamak like the ITER one, you have a view here. You inject a gas mixed of deuterium and tritium. You then an electrical current to convert these guys into plasma. You create the plasma, you trigger the plasma, and then you will have to inject by electromagnetic waves or high energy neutral particles. You will heat this plasma up to very high temperature, up to 150 million degrees. For that, of course, you have to heat then the plasma. But what you would like to do is to produce energy. So in a tokamak like ITER of this size, the desired outcome, the final goal of this ITER project is to be able to produce a plasma with what we call an amplification factor of Q equal 10, which means that you will produce 10 times more energy than you actually used to heat the plasma. And this is only an experimental reactor. For the next step, which is demo, which is a commercial reactor in fusion, the amplification factor is more than 20. It's about 25. But here, clearly, the challenge, once you create the plasma and you manage to heat it, is to contain and shape this plasma. And this is the principle of a tokamak. This is one of the last, I would say, principle I would like you to understand before we go further. The tokamak comes from a Russian acronym, which means toroidal chamber with magnetic coils. So inside the tokamak, you will try to confine the plasma in the form of a donut shape, torus, using very high magnetic field. And for that, you need a set of toroidal magnetic coils, which will generate a toroidal field. Then, thanks to the central solenoid, you will create a second magnetic field, poloidal, like this, vertical, all around the torus. And then the combination of these two magnetic fields in the tokamak will allow to have a twisted magnetic field, like an helicoidal magnetic field, which will actually confine the particles. So this is the principle of a tokamak, and this is the principle of ITER, this torus shape. So this is very brief introduction on fusion, but I think we have as well a lot of things to look at as regard the history. And it's quite interesting to actually understand how you can get to such big project like ITER, really looking at the past. So in the years 50s, the Russian, they discovered this principle of tokamaks, and since the 1950s, then several tokamaks research projects actually emerged all around the world. On the top left picture, you have, for example, the very first tokamak built in France, which was at human size. It was quite small. And since this very first mini tokamak in France, built before the 60s, we have made very large progress. On the other top but right picture, you have here the Japanese tokamak, GT60 Super Advanced, which has whose first plasma has been done in October last year. And this tokamak is the biggest tokamak ever commissioned. Before ITER, of course, because the ITER is not yet built. So this tokamak is the biggest tokamak ever built. In UK, there is another record with another tokamak, which is a jet tokamak. It has been in use between 1983 and 2023. And this tokamak has produced the record in terms of energy produced, with nearly 60 megajoule produced thanks to deuterium-tritium reaction, which are the most effective. In France, we have another record, which is the longest plasma, more than 6 minutes, which is held by the Torsupra tokamak just next door, actually ITER, and which has been recently upgraded into what we call the West tokamak, which is an important test bed for ITER, which is just next door. So actually, you can see that from the 50s, we have made enormous progress in terms of size of the tokamaks and technology. There are very different technology used. In terms of longest plasma, we use supraconducting cores and actively cooled components. For jet in UK, for example, the tokamak was much bigger, but the components inside the machine were inertially cooled only, which did not allow very long pulse. So you'd clearly investigate different types of physics depending on the tokamak you look at. Why we are building a so large tokamak as ITER, whose volume is about 830 cubic meter. It's because the size matters if you would like to produce nuclear fission, clearly. The ratio, this amplification factor of Q, the fact that you can produce really energy thanks to nuclear fusion, is function of the magnetic field strength to confine the particle, the plasma density, and most of all about the plasma volume. So you have here a comparison of different tokamak. I mentioned you the Torsupra tokamak in France, just next door, which is quite small compared to the jet one in UK. And you can see that the gap between this existing tokamak and ITER is huge. It is the biggest gap ever done building a tokamak. And that's why actually we have 35 countries now involved, and that's why we have this so big project now to make this very large scientific and technological gap. I would like to give you some numbers important as regard the ITER project. As I told you, to create the magnetic field, we have different set of field coils and solenoids. The central solenoid, for example, is 18 meter high and about 1,000 tons. The toroidal field coils are quite as high, and they are actually 360 tons each. And on top of that, you have the poloidal field coils and the vacuum vessel, which will actually pack everything. And you end up with a total of 23,000 tons, which is 3.5 the mass of the Tour Eiffel. So it's clearly a gigantic, an exceptional tokamak compared to the other one which has ever been built. So why and how actually we came to this project? I really like to look at these dates and at this history. The Pacific use of nuclear fission came actually from the Geneva Summit in 1985, where Ronald Reagan and Mikhail Gorbachev, they met to discuss about this possible international collaboration for the benefit of humanity. And something like 20 years afterwards, the ITER agreement has been signed in Paris by the French president and all the ITER members, this international project. And they all decided to create the biggest tokamak ever built, all together with this international project. And Cadarache, Saint-Paul-les-Durance, where we are here, has been chosen to be the site. Right after this ITER agreement, France has started to actually level and clear all the work site. It was a nice hill with a forest a bit near to the big Cadarache Atomic Center. And so for 3 years, we were already working there with Laurent. It was only detonations and big trucks with a lot of stones. And after these big 3 years of preparing the ITER site, the construction of the buildings has started. And we are now in 2024. You have here a view of the construction site, which is not very high resolution, I realize now, but it's just to mention that all the buildings surrounding the tokamak, all the auxiliary system are now built, and it just remains now to assemble inside the main building the tokamak itself to start operation. I've put a link here at the bottom of my slides, which is a link to the ITER webpage, where actually you can find a very, very nice timeline with many pictures of all the progress and all the milestones reached inside the project. And this website is quite well done. That's why I just wanted to refer to it if you would like to, because yeah, I've only cited 4 points, but there are much more. So this is for the history and the figure. Before switching to more technique and science, maybe I would like to say a few words about how this international project is organized, because it's quite interesting. As I mentioned maybe before, the ITER project is constituted of 7 ITER members, which represent about more than 50% of the world population and about 85% of the world GDP. These members are China, the Europe, India, Japan, Korea, Russia, and you have the United States as well. What is good is that this international project is as well benefiting for a worldwide partnership as well in terms of scientific results, because clearly the ITER project is benefiting from all the experimental results for all the research undertaken by all the tokamak all over the world of the parties. And for example, for scientific aspects, we have the ITPA, which is the International Tokamak Physics Activity, which is still coordinating some experiments in this tokamak smaller scale in order to really get some answers still in time to build the ITER project, to really reply to some very specific question in terms of, as well of design of components and so on. So that's why, I mean, for me, it's the beauty of this project. It's just this internal collaboration, clearly. So we have this integrated project with a central ITER team, ITER organization, and what we call 7 domestic agencies. Because in reality, the ITER members, they contribute in kind to the ITER program. They actually built the components, and we are assembling all that in the Cadarache site. So it's really an in-kind contribution. They deliver components, they deliver pieces of the machine, pieces of the building, and all that. So to this end, and to manage all this procurement and this manufacturing, each of the parties have created what we call a domestic agency. In terms of cost, it's not equal. The Europe is hosting this project, and it contributes to up to 45% of the cost of the project. For the non-European members, they contribute up to 9% each. And a very interesting point of this project is that all the members they share the full intellectual property of the ITER project findings. Something that I did not write on this slide, but it's quite interesting, that ITER has as well other partnership with countries which are not part of the member. They are called the non-members contributions. We have, for example, Canada. We have Switzerland as well. For the short story, we have the Principality of Monaco as well. I was part of this contribution because Monaco, in order to have some contribution to the ITER project, they are actually funding the postdoctoral researcher. And I was part of this first postdoctoral researcher funded by Monaco. So on top of these big countries, you have as well many other countries who can participate to the project. In terms of who is manufacturing what, it has been shared and distributed at the very beginning of the ITER project in the ITER agreement. Here you have a picture which is not complete, but which can give you an idea. For example, the central solenoid I told you, which is essential to produce the poloidal magnetic field that is built by US. The poloidal field coils, they are shared between China, Europe, Russia, for example. The big cryostat, enveloping everything, has been manufactured and delivered by India. The thermal sheet by Korea. And there is another component, I will not tell everything, but the divertor, which is the component actually Laurent will talk to you about, whose procurement is shared between Europe, Russia, and Japan. So this is to give you kind of a picture of all this international collaboration. In terms of governance of this project, it's the ITER Council which approves the roadmap of the project. This ITER Council is constituted of members, of the 7 members, representative, and they meet twice a year in June and November at the ITER headquarters, which is this building in Cadarache in Saint-Paul-de-Durance. And these ITER members assess twice a year all the inputs to validate the roadmap, to validate the budget, to validate the timeline, and all the costs. And this thanks to different advisory committees, the science and technology one, the one on management, which, for example, give guidance and some assessment of how the budget are allocated or the managerial even strategy of the project. And you have as well the financial audit board twice a year, which is actually looking at all the accounts of the project. So that's it for kind of a general introduction. I will give a very brief overview of some of the main progress, and before we switch actually to Laurent. As regard the recent progress of the project, one of the recent ones in July 2024 was the commissioning of the cryogenic plant. Sorry, we are French, totally. I think you have guessed already. So the commissioning of this brick cryo plant is really a major milestone in the project. We have more than 5,000 tons of equipment installed here, and this plant is very essential to feed the coils, the supraconducting coils, as well as the cryostat, and it's the biggest cryo plant ever built, of course, for Autocamac because of the size of ITER. As regard other big system commission, we have some high-tech electrical procurement, which has been made recently. And one major milestone has been the commissioning as well of the complete water cooling system of the project, which will be soon actually connected to the main building. Regarding the coils, and this is a really impressive achievement because there were many technical difficulties actually, and the ITER Director General already underlined that many times. The 19 toroidal field coils have been completed and delivered to the ITER project, as well as all the poloidal field coils, and that's one of the major achievements, and this was great. Regarding the central solenoid, still in order to very confine this plasma, the CS modules have been delivered, and we plan to have the 6 modules and to continue stacking them and aligning them to build the tokamak by mid of 25, so next year. Again, a nice progress, and actually I would like to finish my talk just telling you that you're really welcome to visit the project. We have our communication team which is actually organizing visit, and when you go into this assembly hall, it's quite impressive to see all that. About achievements, let's talk about difficulties before I finish my part. And let's talk about the vacuum vessels. So the vacuum vessels are different sectors, which when they are built, actually, they will sustain the main chamber where you will actually put the plasma facing components and where the plasma will be sitting. So these vacuum vessel sectors, they have been manufactured and delivered by different countries. And they have actually non-conformities in terms of geometries, because all these different sectors, they have to be finally welded together and assembled, and they could not, clearly because of these non-conformities. So what is in progress and what has been communicated even outside is that this sector's repair is in progress, it's actually in good progress. All the depression along the bevel joint are filled in, and when they are small bumps, they are machined. And this is a massive repair action, I would say, which is going well now. Another difficulties, because they are not only a very nice achievement, but clearly this first of a kind project, this first of a kind components, they made some difficulties. Another thing which has been identified and shared to the community is a leakage identified in the thermal shield cooling pipes because of stress corrosion. And here again, a repair plan is in progress, because this is one of the first steps to continue assembling the tokamaks. So here, clearly, in order to mitigate this issue, the idea and the contract is launched to replace all the corroded pipes of these thermal shields, and as well as another risk mitigation action, a contract to manufacture 3 or maybe more sectors is progressing as well as planned, in order not to put into danger the schedule in case of another issue. We'll finish just this technical part to mention something on safety, because it's our value, ITER safety first, to mention that there are at present more than 300 people working on the ITER site and finishing all the buildings and assembling the tokamak. 90 nationalities difference. We have about 500 European companies. Out of that, 80% are French. And so clearly the safety is a major challenge as well for this project, because we have to manage all these important co-activities with all different nationalities, all different cultures, companies. It's quite tricky and quite challenging as well. It's not only the technical part. And then, yeah, actually, just to finish about perspective, I'm not talking about private and public sectors. Maybe we can get back to this during the question and answers. But it's just to mention that ITER is benefiting from other fields, and they are giving actually spin-off from their findings in different, very different fields. So I'm listing them here, but I think I will just give the floor soon to Laurent. In order to introduce Laurent's part, which will explain you the challenge of manufacturing components, the one facing the plasma, really the closest to the plasma, not all the other plants and not all the vacuum vessel part and so on. I would like just to give you a bit of numbers. So here is a view of the ITER main chamber, where you have what we call the plasma facing components. So the first wall in tungsten, as well as the diverter that Laurent will explain you. During normal steady state operation, this plasma facing component, they receive radiation and fluxes coming from the plasma up to 3 gigajoule for the first wall. And in terms of fluxes, at the diverter part, we are between 5 and 20 megawatt per square meter. On top of this normal operation, when you create the plasma like a torus and you confine the plasma, you can have as well some transients. And we have to design to these transients when, for example, the plasma is crashing, which happened actually when you have some perturbation of the plasma. So the plasma can extinguish very quickly, but when it's actually extinguishing, it's crashing on the wall. And you have to design your components for that. So this is just an introduction to your part, Laurent, because the thermal loads are clearly not the only challenges posed to the manufacturing of the components. So it's your turn, Euro, and I just would like to repeat that you're most welcome to visit the ITER site if you're interested in this project, because it's just so nice to see this achievement. Thank you.
Hi, Laurent. Yeah,
You're
if you could
mute,
come off
Laurent.
mute.
Yes, thank you. Thank you, Sophie. I was tidying up some details, like going to full screen. Thank you very much for this opportunity. Thank you to the IET for having me tonight to talk about the ITER, in particular for the internal components and the divertor. Laurent Ferrand. At the moment, I'm working as a coordinating engineer for the divertor project. I'm a long-time employee of IO, just like Sophie. I started around 2009 as a staff, but I was before that already orbiting around the project for a few years. In the beginning at IO, I was mainly working on the design of the divertor, and I've been lucky enough to now work on the production of the divertor. So I will try to give you some slides about this magnificent component that I love. So yes, the very quick abstract of the slides that I have prepared for you today. So this is basically an introduction about why is it such a challenging environment for the divertor to sit in the ITER machine. So this is a place where you have extremely high heat loads, you have extremely high electromagnetic loads, you are facing neutron streaming, and you have to handle you have to be, let's say, compatible with operating in the vacuum while considering all these other constraints. So this is pretty challenging on many levels, at the level of design, at the level of manufacturing. So in the next slide, I will tell you a bit more about particularly operating in vacuum, under the EM loads and under nuclear constraints, and in the end power handling, because I think this is the most challenging for internal components. So a few words about vacuum. In the ITER machine, we have extremely high level of vacuum, which is basically the density of the primary vacuum is between 1 and 10 million times smaller than the density of the atmosphere. So this is really, you don't meet a lot of atoms in this vacuum. It's pretty high. And the ITER is one of the biggest and most complex vacuum, let's say, facility ever produced, ever built, with several levels of vacuum. Of course, the one, the highest vacuum is the one in the VV, in the vacuum vessel, the place where we run the plasma, but we have also different levels of vacuum. For example, in the cryostat, which is the big tin can that you see now on the screen on the left side, there is already a certain level of vacuum, which is pretty high, just to allow the superconducting magnets to operate in a proper conditions, because superconducting magnets have to be very cold to be superconducting. On the left side, you can see one of the torus cryopumps that are creating this, generating this primary vacuum in the vacuum vessel. So this is quite an impressive feat for many things that I will be showing in these slides. It's the biggest ones ever produced. This is typically one of the examples. So the particular one that we see on the picture is actually the first one of the series production run that has undergone factory acceptance tests successfully, by the way, in May this year. So for the internal components, operating in vacuum leads to, let's say, raises two main concerns. The first one is the cleanliness, and the second one is the leak tightness. I will talk a bit more about that now. So on the top left side is a very nice picture that I like very much because it looks very vintage. This is actually out of these 6 guys, I think 5, oh, actually 6. Yeah, the 6 of them, they were working at JET at some point in time. And the ITER vacuum group has an immense depth to the JET, the Joint European Torus, which is now under decommissioning, but that has been operating for something like 40 years in Cullum in the UK. Okay, so these guys, they have put together a vacuum handbook, which is essentially giving rules for anything related to components that have to be operating in the vacuum, including rules for the design, manufacturing, assembly, handling, everything for the various quality classes of the vacuum. For the cleanliness, why are we bothered? Because as I was mentioning earlier, there is a very high vacuum in the vacuum chamber when we operate a plasma, which seems a bit counterintuitive, but this is like that. And we don't want to have any pollution in this plasma. How do we avoid that? By having extremely clean components. Because when we have plasma running in the machine, there will be convection of heat flux on the components that's going to cause outgassing in the case where the components are not perfectly clean. So for that, there is no secret. The particular attention shall be paid for the cleanliness at all stages. But how to ensure this is by performing all activities in clean rooms, having a clear clean work plan that has to be issued before any activity can occur. Proper cleaning procedures approved by our gurus over there, and also the prior approval of the fluids and material, because we want to avoid those that potentially could outgas or that could not be suitable for any other reason that are related to another topic I will talk about, which is the neutron flux. And then we need to use just approved procedures and techniques from the handbook, or we have to follow proper qualification method for novel techniques, which happens on a regular basis. Typically, at the moment, people are very busy with qualifying additive manufacturing for vacuum application. And then we want to have a component that is leak tight. When I say leak tight, it's crazy level of leak tight, because the picture that you see, the picture that you see on the bottom left, this is a component equipped for hot helium leak test. This one is the cassette body. And the picture on the bottom right, this is thermal vacuum test chamber in the French site of Thales Alenia Space in Cannes. In this place, they normally test spacecrafts for leak on the various, let's say, tanks that they are bringing to space, but they are concerned about leaking fuel typically, and they will be looking at leaks in the range of 10 to the -8 Pascal cubic meter per second in nitrogen. And we are looking for leaks that are 2 orders of magnitudes lower. And also we are looking at leaks in helium, which is a significantly smaller atom. So basically what we are doing with this test and this criteria is making sure that the component is absolutely leak tight, because this is very close to the detection level, let's say. It's quite high to get this, it's quite difficult to get the sensitivity for this test. Now I'm going to talk to you about the EM loads a little bit. So the magnetic field of the Earth is about, as you can see, a very small portion of a Tesla. And in the machine, we will have anywhere between 5 and 10 Teslas at any time. So this is very, very much higher than that. And this leads to very high electromagnetic loads on the internal components. What I mentioned here typically is that we have relatively high hydraulic pressure in our components, because they are hydraulically cooled, actively cooled. But because of these very high electromagnetic loads, actually our primary loads are the EM ones by a factor of almost 10s. Typically, the the level of the EM loads applied on the internal components is anywhere within the range of 100 tons for components that are just a few tons. So this is due to the fact that we have a lot of energy stored in the magnets, the superconducting magnets, toroidal field coils and poloidal field coils. In the case where we have transient event or disruption of the plasma, this energy is several gigajoule, and it gets converted very quickly, and it results in very, very high EM loads. Also, these loads are cyclic, so as a result, it represents quite a big challenge for the internal components. And the way we deal with this is we have developed our own criteria for the structural design of the internal components, and we do thorough structural integrity verification of all our components. And we also have quite a lot of requirements for the quality of the material and techniques that are implemented in the fabrication of the internal components. For example, we have quite tight requirements for the micrographic examination and the volumetric non-destructive examination of the forgings or plates. We also have strong requirements basically to exclude from the material any trace razor or any inclusion that could be a precursor for leak path. We also have very stringent requirements for welding and non-destructive examination of welds, as well as actually the qualification of the operators and inspectors. And we have in particular 100% volumetric inspection requirement for all welds with that represent a vacuum boundary with quite tight acceptance criteria. Another thing that happens in the tokamak, and actually that we are trying to achieve, is a fusion. So unlike the process of the fission, the fusion generates fast neutrons at 14 MeV. I'm not going to go too much into the details of that one, but just to tell you, we have fast neutrons in there. What's the problem with fast neutrons? It's going to activate some nuclides in the bulk of the material of the machine, and it's also going to impact the structure of the material. We have a unit to measure this. It's called DPA, displacement per atom, because of the neutrons arriving so fast and disrupting the structure of the material, and this is detrimental to the mechanical properties. And the way we deal with this basically is by making sure we select the proper material. We avoid those with radioactive isotopes, of course, and we have specific radioprotection requirements in terms of low content of niobium, tantalum, cobalt in all the bulk material that we use in the machine. Regarding the DPA, what we do for the irradiation effect on the material, also we select the material that is suitable, but we have to consider this in view of the research plan. And this is a problem that is clearly identified for the next steps in the development of fusion, because the fusion in a power plant, you need high level of availability. So you need to have long time of operation, which is not the case in an experimental machine as ITER. So we need to have structural materials. Basically, all irradiated materials have to be suitable for the higher level of neutron fluence. Yes, another one of the key aspects that I didn't mention it at the top of this slide. It's basically ITER is a nuclear installation. It corresponds to a classification in the French decree, and we have to apply the ALARA principle, which is as low as reasonably achievable. and that's one of the reasons also why we have to limit the activation of the bulk material. Okay, and now going to the heat flux, which is the most interesting part. So we have this this machine where we basically have the hottest, more or less the hottest temperatures in the universe and the coldest one within a few meters of one another. So that's pretty funny. And this heat is compressed away from the wall by the powerful magnets, but we still have some convection. And also at the level of the divertor, we have direct strike from the plasma in a region that we call the strike point. You could have guessed the name. Basically, when you are sitting on the beach on a sunny summer day, you will receive about 1 kilowatt per square meter of heat flux from the sun. Now, if you're a space shuttle and you re-entry and you are on the re-entry from your flight and you hit the atmosphere, what the heat shield will see is something around 0.5 megawatt per square meter. In the ITER machine, we have heat fluxes in the range of 5 megawatt per square meter for the blanket and between 10 and 20 megawatt per square meter for the divertor. So you see it's up to 40 times higher than the space shuttle re-entry. I like this image. I think it's very telling. Oh, okay. So now what you can see on the right is what the plasma looks like in west. So let me go back and run it again. It's just 7 seconds. On the left side, it's a picture, infrared picture of the inside of a jet, actually. So this is just to give a bit of illustration. Now, as you have seen on many of the pictures that we have already discussed, the machine geometry is torus, but the magnetic geometry is not torus, actually. It follows intricate geometry with field lines, and the particles have a tendency to follow the field lines. And for the divertor, typically, and in particular in the strike region, we have particles following these field lines that are going to be deposited directly on the targets because the geometry is intersecting the field lines. And this is why we have such a high heat flux, as I was mentioning before. So how do we deal with this? We have two main techniques, two main design. We have the hypervapotron. Hypervapotron in the divertor is used in the dome, this component that is manufactured in Russia, and in the first wall. So this concept use tungsten tiles as armor material, and this is based on the copper, chromium, zirconium, and the 316 nanometer grade substrate. And then the geometry of the hypervapotron provides a good heat removal that is suitable for the level of heat flux that is expected there. Now, for the vertical targets, which are the ones that, as I was mentioning before, are intersecting the field lines and receiving the heat flux up to 20 megawatt per square meter, we have a different concept, which is the monoblock concept. So this one is based on a block of tungsten with a hole in the middle, and then you have a smooth tube in copper, chromium, zirconium there that is passing through all the monoblocks a little bit like a skewer. And also we have so-called swirl tape that is providing some agitation in there in order to prevent a laminar flow. And this is how we manage to extract up to 20 megawatt per square meter. So this is very critical because if you have a failure of one of the units on one of those components, then you will very quickly get degradation of the tungsten, and it's going to pollute the plasma. We want to avoid that, so we need to control very precisely the continuity of the quality during the production. One of the ways we do that is by doing so-called high heat flux testing. So basically what we do is we extract some components from the production line and we send them to a testing facility where they will be put under 800 kilowatt electron beam gun that is going to hit the surface. We do a thermal mapping. We do heat cycling, several hundreds of cycles, very high heat flux. And then we do a thermal mapping again, and we detect evolution of the defect or any other indication that could tell us that the quality of the production is degraded. Another way another important point for the let's say the handling of the heat flux is the very good alignment of the surfaces, because this high heat flux, if it's deposited on the top of the component or let's say the small element that is in front of the plasma, for example, here on the right side you can see monoblocks. The monoblocks are very efficient at removing the heat when it's heating on just one surface. But if you have a leading edge in your design, in your component, then your plasma will be deposited on two edges at the same time. And this is something that we have to avoid absolutely, because the heat, the temperature will increase very quickly. And even though the tungsten is the highest, the metal with the highest melting point, it will eventually melt. And this is something we have to avoid. So how do we avoid this? We have very strong requirements in terms of dimensional inspection, with a dimensional metrology handbook that was developed by the metrology group at IO. And we have to ensure that these requirements are followed for every component. A few notable mentions, let's say, in terms of challenges. So as Sophie was mentioning, this is a very international multicultural project, which is very good for fostering peace in the world, but that sometimes can be not ideal in terms of organization for a project that has to deliver with tight milestones and strong technical requirements. So we are navigating this world. One of the points typically is the various normative environments and standard frameworks depending on the country. Sometimes they are equivalent, but what you get in an ISO is not necessarily what you will get in a JIS from Japan or a GHOST from Russia. So it takes time to understand the equivalence between standards and frameworks. Integration is also quite a bit of a problem, because even though the ITER machine is so big, we have a lot of systems that have to be integrated there. And sometimes we end up lacking space, even if with the huge size of the machine. But all in all, today we are, for the divertor components, starting the series production for all of them. And this is a very, let's say, very challenging phase, the beginning of the series production, but we have the feeling and we see the sign that the lessons learned from the prototyping phase have been efficient, and that we are now progressing full speed in the production of the series components. And I think that's, yes. Thanks for your attention.
Thank you, Sophie and Laurent, in that. I think it's time now to hand over. I'm sure there'll be a few questions, so I'll hand over to George, who's been monitoring any questions and perhaps can put some to you. George.
Well, I'm going to make a plea for questions now. Please raise any questions using the QA panel. And to start the ball rolling, can I ask a question of Laurent, please? Clearly, with success with ITER, with very high neutron flux, that can be a very damaging environment. What are the key principles within the ITER design to manage that neutron flux into certain parts of the confinement device and to dissipate that heat?
So we indeed we get neutrons first line, I would say, in the divertor and in the blanket. This is typically handled through validation by calculations for the management of the additional heat flux that is received from, let's say, not heat flux, but heating that is due to the nuclear heating, basically. But I would say that in ITER, because we have intermittent activity, this is not the same concerns that we would get in a production plant, where you would have much longer duration of the operation and much higher neutron fluence in the end. What we are mainly focused on and worried about actually at ITER is the streaming of neutrons in the magnets, because these magnets have to be very cold in order to be superconducting. So if we have neutron streaming and we have a hotspot somewhere on the magnet, the magnet could lose its supraconducting, let's say, nature or property. And this is an event that we want to avoid at all costs because it's a cause for disruption. So I would say that this is for the problem of additional heat input. This is managed by design and verification. For the problem of streaming, this is also something that is taken care of by a special group that we have here at IO. We have a nuclear analysis group, which is also combined with the design integration group. And these guys will be the ones verifying that we have no neutron streaming between components that could be detrimental to the magnets.
Can I make another plea for people in the audience to raise questions via the QA panel? And meanwhile, I'll try asking a supplementary on that. And however effective you are in managing that heat, there will be damage to the vessel and there will be damage to the walls and the diverter. How have you designed the device to make this manageable, to effect repair in life? And what assumptions have you made about time to failure and time to repair?
So this is building on let's say two sources for this information. Basically, there's material for which that have been around for a long time, that have been used in the fission industry or in other for other R&D purpose. The literature is there. We know what is the level of dPa, that is displacement per atom, that I was mentioning a bit earlier, that is acceptable for this material. And then we select the material which is for which we have a compliance between this capability to accept neutron fluence and in front of the neutron fluence that it will see during its lifetime in the machine. So this is how we manage for the material for which there is no literature, which is, for example, recently we have found out that there is no literature regarding fiber Bragg's gratings, which are fiber optics based substrate that we use as in sensors, for example, for linear displacement sensors or other type of strain sensors. So considering that there was a lack of information on this material, we have launched a a collaboration with one of our non-party members that Sophie was referring to before, which is Kazakhstan. And we have a program for an irradiation campaign of fiber brax gratings in this in one of their actually in two of their nuclear reactors with high fluence, so that we can get the certainty about the time that let's say the lifetime that we can expect from this material in the ITER machine.
I see, George, there's a couple of questions. I don't know if you can see them from Steve Cooper.
Right, okay.
Shall I just cover them? He asks in question 1.
Right, I've got it. I've got them. Yeah, okay, I found them.
So I'll just ask the question.
You go on.
Did I understand that energy is harvested out of the system via the diverter strike points? Presumably the strike point is where then transfers the heat to a fluid. That seems to be a sort of technical question.
Tu la prends, Sophie?
So no. So your question is how we will actually absorb the heat and produce energy, maybe in a reactor, in a commercial reactor. It's more by because of the neutron heating to the actively cooled block shields actually, and then you will extract this heat and then generate energy via steam generator and so on. Unless I don't know, you would like to complete. But it's that the diverter, the role is more, I don't know, maybe we can show a picture again. It's more really to support the legs, the 2 legs of the plasma. Clearly, you're confined like a donut, and you have these 2 strike lines in a cut, these 2 legs. And with this diverter configuration, we did not actually explain much about all the physics, but what you will extract are the helium ashes from the nuclear reactions, because these nuclear ashes, they have to be extracted actually. So the diverter is there so that the plasma sits down clearly, and you have of course some heat fluxes, which are not the one which will be used for commercial reaction, and then you extract the helium ashes, and it's as well here where you inject the gas. It's really kind of a functional components to really allow nuclear fusion reactions to be triggered, but it's not where you will extract the heat. You just actively cool just to try to sustain what you will face actually. I don't know if this replied to your question.
I think that is a reply to that question about the diverter strike points, and I think that you have answered that in terms of the transfer of the heat to fluids for the cooling system. Mm-hmm. But Steve also says your description of the whole build describes a hugely complex system. Mm-hmm. And he asks, do you envisage a future commercial realization, I guess when you're moving towards demo, that could be simpler and more economically built once the configurations that are required are better understood?
Yes, clearly. So in terms of dimension already, this is the huge gap I mentioned from the ITER tokamak compared to other tokamaks. You have a factor of 30 in terms of size, in terms of many things. Demo will be just a few percent, maybe 10% larger than ITER, so that the big gap, the big experimental gap, you have done it. And then everything that you will have investigated with ITER in terms of the perturbation of the plasma actually when it's extinguishing, shutting down, whereas you do not want to, or some magnetic perturbation, all that will have been investigated. What you will aim at demo is a nice steady state plasma. You will not need to have all the diagnostic systems. The heating system will be as well be optimized. So the objective after ITER, which is really a research, an experimental reactor, will be to simplify some parts of the design. And because it's commercial, you will have not all these many features which are quite challenging and tricky to manufacture and to integrate. It will be a simpler tokamak. It should be. This is the point.
Osama Salim has asked a question, which I think is in an area that you raised, Sophie, and Osama says, as with nuclear fission, isn't this dangerous in the case of malfunction. Chances may be low, but consequences could be very bad. Perhaps a little bit more elaboration of your rationale for the safety of nuclear fusion versus fission might be helpful.
Yes. So for nuclear fission, you actually, how can I say? You're actually breaking nuclei, and this nuclei becomes unstable. See this instability actually, which can react, which can then provoke in-chain reaction, runaway reaction, and so on in fission, and then you gain more and more energy production, more and more neutron, and then you have this big issue in fusion. Actually, when you are making fusion reaction, it's stable. You do not have this instability. It's clearly not the same physics process, and it's stable. And when you actually shake a bit the plasma or perturb a bit the plasma, some perturbation, you just extinguish the plasma. So it can crash on the wall. It will create damage, for example, to the divertor or to the first wall, because locally you will actually release a few gigajoule of energy on components. They will melt locally. They will have some electromagnetic loads, so they can be a bit damaged, but it cannot provoke this unstable in-chain reaction. The plasma is really fragile. It's a bit like a gas. Yeah, it's the fourth state, but yeah, I don't know. Stability of the nucleus, I would say.
Thank you for that.
I would say that maybe if I can just compliment a little bit, it's the major difference between fission and fusion. In fission, you have tons and tons of fuel sitting in the same place, and if you don't control your reaction, it has this possibility to become out of control and create these accidents that we have already seen in the past. Fusion is different. Fusion works a little bit like thermic, like the engine of a car. If you stop feeding the fuel, then it stops. So then it can stop in a more or less hectic manner, as Sophie was mentioning. You can have disruptions where you will have your plasma crashing on the wall of the vacuum vessel and very, very high electromagnetic loads. But we calculate for that, and the main point is that the amount of fuel that is present there in the machine at any given time is so small that it cannot. There can be no loss of control of the reaction. The only loss of control that we will have will lead to the reaction shutting down. But there is not this risk, intrinsic risk of fission, that you have a lot of fuel fuel there in the same place at the same time. In fusion, it's not like that. It's a few grams at any given time.
Thank you. I have a question from David Levine, who asks, when are you hoping to start the pump down on first runs?
So first plasma date, yeah, I don't know for the first plasma date, no, because yeah, well, it's really about the schedule. So about the schedule, it's a bit tricky to answer. There is a new baseline exercise which is ongoing. I do not pretend to have all the details, because all these details are actually discussed by the top management and the ITER Council. The formal date which has been given, it's 2034.
Yes.
Yes. And then there was an optimization. The previous first plasma date was supposed to be just a few kiloamp plasma. Just you turn on clearly the machine and then you stop everything, and then you assemble all the in-vessel components, actually, like the divertor, the first wall, and all these things. What is planned now to do is that you do not start with this first plasma, a few kiloamp, but you actually build a really quite solid and complete machine before turning on the machine, and then you never stop. and then you already start running quite energetic plasma. So the first plasma date, the symbolic date has been pushed, but the idea is clearly that actually you start the first plasma in 10 years from now with a complete machine, instead of switching off a plasma, stopping for 5 or 6 years, assembling the rest of the tokamak and restarting operation. And this is the new baseline, which has been discussed. So you have this first plasma date. There are much more details now discussed at the top management. And then we will have a first experimental campaign, which is called SRO, for Start of Research Operation, which will quite high experimental goals already. And there will just be a switch off to change the first wall to an actively cooled one to go to the very efficient deuterium-tritium campaign later on. So first plasma in 10 years, but in the meantime, we assemble everything. We do not wait with our components outside.
This is a semi-philosophical question that the project has been facing, and I would say that any big science project has been facing. How do you maintain engagement of your stakeholders, but at the same time continue to have a meaningful research program? So if you want to maintain the engagement of your stakeholders, you have to have milestones that are not 10 years in the future. You want to have regular milestones, and people get the feeling that and the perception that things are progressing.
Okay. Have we lost some sound here?
No,
okay.
I think we lost the connection, no?
No, we're okay.
Okay. Okay. Yes, so previously we had the so-called first plasma that was, as Sophie was mentioning, okay, you just pump the vacuum, you do a small plasma like in a neon tube, and then you have to shut down for 5 years because you have to actually mount your components in the machine. And this is the things that I like with the new baseline is that we do starts of research of operation with a machine that is that will allow us to progress much more in the research plan.
Presumably you'll be phased and you'll do hydrogen plasma, then move to deuterium tritium when you're ready. There must be a period over which you will pump it down, and then you will go through a set of trialing phases as well. So that could be quite a period, I should imagine.
Yes, absolutely.
Yeah, the start of research operation, the first experimental phase, it will be helium and hydrogen, and then deuterium plasma to really control the neutron activation. And then we switch off. We are able to dismantle some parts, and then we mount the actively cooled first wall to switch to this deuterium-tritium operation. Exactly.
I have a question here from David Bauer, but I think if you'll forgive me, I'll shift that one a little bit because I'm a bit closer to some of these things than he might have seen. There are a number of commercial fusion reactor experiments which are running now. How do these sit alongside ITER in terms of the way in which the research understandings will influence each other, materials or whatever? And I'm thinking of things like spherical tokamaks and from some of the commercial organizations as well.
Tu es mute, Sophie.
Too late for us. Sorry for that. Yeah, so I put some slides in the backup because it was clearly I was too short of time to talk about that. This private public. I participated to a conference with colleagues recently, which is a symposium on fusion technology, and it was my first conference for a long time and I clearly see that the private sectors were quite present, and it's actually great. There are some synergies. There are a lot of collaboration and discussion done between all these sectors, even private and public, during conferences. as regard ITER, I don't know if I have this second slide. So we have different, many different initiatives, either private, even in public. You do not have only tokamak, you have stellarators, which is totally another concept. And here, actually, the ITER Council has asked last year to really make some engagement with the private sector. So there was a very first workshop which has been held at ITER in May this year with more than 350 participants, and where all the private sector's company were actually attending in order to try to exchange as much as collaboration as possible, exchange data, because all this initiative, it's okay, it's other money, it's other investment, but it does not mean that you're fully in competition. We can all benefit from each other. It's like all the tokamaks built all over the world. The Jet one was inertially cooled, not the same size, not the same technology. You combine with West, actually, which is actively cooled, supraconducting. You combine all these actually findings and you can build ITER. And for the private sector, there is clearly a wish of ITER to establish channel with the private sector. And to share as much as knowledge as we have actually with these private sectors. So it's just a slide here to summarize a bit of initiative which has been undertaken. And yeah, and just to give an example, at recent conferences, I discussed a lot with colleagues from Spark, from STEP. So Italo exchanges, it's quite interesting.
So can you help me by explaining some of the key differences between the ITER approach and these smaller spherical tokamaks?
In my field, for example, the plasma-facing components, they do not have the same approach at all in terms of design. They do not have the same approach at all in terms of maintenance and shutdown of the machine. On ITER, for example, because clearly the experimental days will be so expensive, we really plan to build very, as actually Laurent has demonstrated, I would say solid, very reliable components, and you go to a very big scale right from the start to produce as much as fusion energy as possible. The other tokamak, they are smaller, they are using a smaller plasma current, but not necessarily the same mix of species or heating system. As regard what they target as objective, as ITER is planning the Q=10, I will not. I do not want to give my opinion on their actually reaching their objective or us reaching the objective. I think I have clearly the humility, not knowing if we really reach what we would like in time. The only thing is that we can just benefit from all these different approaches. It's very difficult for me to give you a comparison. It's so different in terms as well of organizational structure. I don't know about their auxiliary system all. So I don't know, Laurent, if you know a bit more about STEP and Spark, for example, or even the...
Not specifically about them. I would say it would be, there's quite a lot of such initiatives that have sprung out a little bit everywhere recently, because there was a huge influx of money towards nuclear fusion startups, in particular in the US, but not only. We have one in France, for example. It's called Renaissance. My feeling is that they build their strategy around a specific concept, but very often when you look at their development plan, they have a very precise first step, but then very quickly for the next demonstrators, you can notice that some important bricks are missing, that they miss technology or development that is not already there. So it's really an ecosystem. I think what they plan on is basically to build on the progress of also their competitors. That's why for me it's not really a competition. It's really some sort of ecosystem that is growing together, let's say. And the approach of ITER towards this, the private sector, is to be collaborative and to be to support as much as reasonable, I would say. But I could not go into each individual concept because there's so many of them. There's really a wide variety of different systems.
We are just meeting them, trying to, and it's good.
Okay.
Well, it's not a competition, but at least it allows to challenge the ideas, which is always interesting, actually.
Yes.
Good. Can I take you back to some questions about ITER? How is the useful energy produced harvested from inside the tokamak? This from Neil Penhaligon. How is the useful energy produced harvested from inside the tokamak?
Sophie, I don't know if you want to show something, but this is, I don't know who, I was reading something recently, and some, it was some sort of nerd type of forum for engineers, and it was a meme actually, and the guy was, so it was, the image was this cat that was looking, and so the text was new method of producing energy. You open the box, and in the end, it's boiling water. So this is also what we are going to do, essentially, just like everybody else producing power at the moment, except solar panels and windmills. But essentially, when you want to have a concentrated, powerful source of energy, you will always end up heating water. So that's what we will do.
And from Faris Ismail, how are the integration interface conflicts resolved? With the blanket and diverter, different diagnostics, etc. Who has the final say?
That's very interesting. A very interesting question. I would say that there's always a conflict because we want to build ITER. We want it to be efficient and powerful, but we also want to learn a lot from ITER. So if we don't have diagnostics, we cannot learn anything from the operation of the machine. So there is always a fight between those who are working for the systems and that tell to the diagnostic people, okay, deal with it. If you are not happy, we will just not mount your system, and then the diagnostics will complain. I'm exaggerating, but just a little bit. No, this is a very regular source of friction, I would say, that the systems will clash together, or they have to have a line of sight, and your component has manufacturing tolerances, so there is a risk that you will hide the plasma from these detectors, for example. One also, I would say, major issue that we have with the integration at the moment, which is linked to the fact that the diagnostic systems are so high-tech and still under development, is the fact that we have very regular changes in the design of the diagnostics. And if you have components under series manufacturing, and then you have an interface that changes, this is sometimes can be impacting quite significantly the production of your components, because you have to stop, evaluate the change. Maybe you have to implement the change. Maybe it's too late because some components are already too far in the manufacturing route. That's that's not the easiest challenge that we have to face, integration. Yes.
Question from Oliver Buxton.
George, could we make this the last question, because time is moving along?
Okay, so last question. From Oliver, what temperatures do you expect to see on the components on the inside of the tokamak if the plasma is 100 million degrees? And do the components ever get damaged?
Oh yeah, they get damaged even in smaller tokamaks. So at ITER, for example, at the target, I think that the maximum temperature we expect is 1000 degree. what we really do not want to reach is this 4,400 degrees, which is a melting point for tungsten. It can happen it can happen locally in case of transients. You have a big release of energy and some picket fluxes somewhere. For the first wall in tungsten, it will be the same. The temperature of the first wall will be much lower. It is actively cooled between 70 and 100 degrees, and during operation, you can reach locally more than 500 maybe at the most. But yes, of course, when the plasma is crashing and you're actually melting, you will reach above this temperature of melting, but quite transiently. But it's not 1 million. You do not have usually vaporization. It's more melting anyway. And it's managed thanks to the confinement, because the plasma is very hot, but it's confined in these donuts. And then you have some very fast decay of the loads and the temperature profiles and density between the wall and the confined plasma. Yeah.
Lovely. Okay, sure. I think we should call that a day there. So I'd just like to say a very big thank you to Sophie and Laurent for going through all of that about ITER. I learned so much, and it's such a huge project. I think it's amazing that you know, and all these questions which talks about the integration of the components, that just must be a huge headache to get all this stuff right. And you can understand why a project of that size is just taking so long, but very interesting. And I'm sure you have a great time working in an area like that. So again, thank you from the IET Anglian Coastal Local Network branch, just giving up your time to talk to us tonight. Very interesting, and I wish you all the best at getting this thing working. Because
thank you very much, and thank you for the questions. They were great. Thank you.
Thank you.
Yeah, I'm going to share my screen now just to cover off a couple of events that we've got coming up. But we can say this one has actually finished. So thanks for all those attending. I'll leave the screen up with the share on, and we'll have a look at that if I can find it. Where's that gone? Is that because we're still sharing a screen? Someone is there? No,
I don't think so.
Right. Okay. So my share isn't actually working at the moment, so we might have to just knock that on the head. I don't know why that's suddenly gone wrong. Anyway, so we do have events coming up in the very near future. On December the 4th, we've got an event which is going to be more local to Suffolk. We're moving from the south of France back to Suffolk, and that's going to be The Future is Arriving, and the subtext is Even in Suffolk, and it's going to be a talk given to us by the Suffolk County Council's Chief Sustainability Officer. So he's going to talk to us about how he's trying to move the citizens of Suffolk to use more sustainable energy and how the council is helping to do that. So hopefully we can have a good audience in Ipswich in the atrium at the University of Suffolk to listen to Peter Frost talk us through there.